And so we met at a Mexican restaurant. The professor who was the coordinator of the math, of the Master of Arts in Math, he was also teaching the class. And so he bought dinner. He was very generous. He bought supper for everybody. He bought a few pitchers of margaritas because everybody was an adult. And that was our final.
Yeah, something like that. I don't mind doing that. But again, see, we want to be very careful that we shouldn't be really not like administration, nothing, right. No one should be, it shouldn't become the talk of the town that, oh, these people did this.
Exactly.
Yeah. Like I wouldn't like to offend anyone. But yeah, this is, yeah, something like that. I would like to open up. But again, let's be careful. But talking about your exam, like the author of our textbook, Schwinger, like he was Nobel laureate, so he could afford to do these things. So he had a student, I think the other author, Milton, right? So that's his PhD defense, and the committee gets together. So what do we do? And they just go out for dinner, or lunch actually, have a lunch and come get back. And yeah, that was your PhD defense. So not just an exam. Yeah. So I think when you're really an authority, then you can afford to, and sometimes when you know the person so well, I think there's no need for the formalities. And I think I feel that this course should go fine. I think everyone is doing fine, and the final exam may not be an important component of the grading for me. So if that is a motivation, yeah, surely. Yeah. But yeah. Jordan, how are you? You don't seem very. How are you? It's brighter out there. Very tired, yeah. Are you working before this?
Yeah.
Thank you, Moses. Oh, I should change this.
Like a lot of
There's a lot of
minerals.
yeah.
Oh, probably plaster from the.
Yeah, probably that's what it is. Yeah.
So we have this is not false ceiling is leaking. It's condensation due to that. We have a lot of fog here. What are you, cloudy day? Yeah.
Yeah, it seems. We also had a lot of rain the last couple of days.
Well, that also could have contributed.
Yeah.
Your place seems pretty bright, so you don't have a cloudy day, I suppose. At least the background seems.
I think it's because of the angle you're at. Typically, it's kind of. It was sunny this morning. It has since changed some, but I think this is more of the normal angle. It's probably a little darker. Oh, your face kind of towards. But it is kind of bright, I guess.
Kind of bright day, yeah. Okay.
Even though it is kind of cloudy. Weird.
There are others. The grading is collecting in this course, all my courses. So, get to it, but we can maybe.
It must be because in at my school, I'm having that same issue.
Your grading? Or?
My grading is also building up a little
There
bit.
must be some chain.
So it's
I think a lot of people this time of the year, normally spring break's rolling around, right? So usually there's that week that you have to like catch up, I think.
I had spring break. I felt more overwhelmed with work on spring break than had I just been doing regular stuff.
Oh, did you actually have spring break at your school?
My school did, because we're not a commuters type of school. It's a very people aren't going anywhere really.
Yeah, even the community college here, they have a spring break, so they didn't have any like us. So yeah. But my problem was
The college,
yeah. Go ahead, John.
go ahead. Oh, okay. The college in my hometown, there's a lot of, I guess the students are, a lot of complaints about not having spring break, just as like a recovery period.
Yeah.
I guess there's like a petition on the campus to give them a spring break, even though it's not in their schedule.
Which college is
So
that?
they tried to give them like work 3 days, like every other Friday or something for the.
Which
They
college
tried
is
to
that?
come up with some solution. I'm not sure what. What's that?
I said, which college is that?
Which college?
Yeah.
Southeast Missouri State. Yeah. I think I don't know. They have like a forum page on Facebook for the university, and it used to be a good thing, but I think it's more become a place to complain about different things of the university. I've just been following it since I've been there, so it's interesting. But you know, even if like, oh, they didn't give me enough lettuce in my salad at like the local. It's turned into more of a place to complain. Or originally it was like a nice place where you could go and say, maybe it would be best to move this parking spot to this other space because this car sticks out in the road every time in this one parking spot. Or just like give good suggestions to the university to look for fixes to help students. And then there were some good ones, like there was a student that was legally blind, you know, could see, but legally blind, where some of the crosswalks they were hard for her to see. So she gave some suggestions to like a brighter style paint that would make it, you know, for students with those sorts of needs. So it was good like that. But now it's digressed, I guess you could say, into more of just a complaint about everything. So right now, the spring break is the big complaint. I guess students are feeling overwhelmed. Who knows?
Yeah, where is Luke, by the way? 1, 2, 3, 4, 5.
Maybe he went on spring break.
APS.
He went on space.
I don't know when his
Oh
APS
yeah,
presentation
he
is.
must be on APS. Yeah, so let's not wait for him. Yeah, that's what must be. Good that he's going to. Okay, anything else interesting? Nothing. Okay. It should be set, I suppose. Oh, oh, how was the homework? Could you finish the homework? Yes, no? No, you said no.
No.
Yeah.
We've been looking at it, and it's,
Yeah, you can take more time because the next homework is not nearby. So, homework 6.
You were gonna have it due, you mentioned last week, maybe on Thursday.
Thursday, okay, yeah, I can make it, yeah, actually, let's make it Thursday because there's the other homework, even though it's not due, you guys will never open it otherwise, so probably you'll never open it anyway, it's not due. Look at it though. So this is not due, but this is relevant, okay, not due, but relevant. Is that correct word, relevant? Spelling?
Yes, has value.
Has value.
Relevant. That's what it means.
Oh, yeah.
Like it's
Oh,
important.
yeah, yeah, that's correct. Yeah, relevant.
actually, homework 6, the last Thursday, you had already changed it to Thursday.
Oh, I did change it, is it?
Yeah, it was already changed to Thursday verbally.
Oh, yeah, verbally, yes, that, I think that I roughly remember, but there is a chance that on G2L, these dates might be locked. So whoever has the first experience, just shoot an email. If I forget it, I'll try to remember this. And I postpone it. I might postpone it all the way to 1 week or so because there is no homework there. But take the deadline as Thursday, let's say, okay? But I'll allow late submissions. And there is a midterm coming. And I was wanting to be hard a little on the midterm. So this is going to be in class and no Zoom, right? So we will get to see Jordan in class. Okay. That's all. Yeah, so we introduced the Lorentz transformation, and we should talk a little about that. This is all, you see this at undergraduate. Oh, here, Luke is here. We thought you were stuck in APS lobby. Okay. You guys had to take a hike. Yeah. Okay. So we introduced the Lorentz transformation, and we should talk about some implications of that. We see that we see this, at least whatever I'm going to do in the early part today, in pretty much popular stuff, popular physics, if not undergraduate physics stuff. But still, I will go through it for completeness. But I want to go a little more on the details of the space-time diagram. Hopefully, it might be useful. But again, most of this, whatever I'm going to do, is undergraduate stuff. And from the response I received in the last class, I felt I should spend more time on this, even though I was, in general, I usually keep only 2 lectures or something for this. And we will talk about the actual kinematics, basically do the whole of introductory level physics. We do Newtonian physics, right? We write F equal to ma or we learn how to use force equal to mass times acceleration in undergraduate physics. We want to do that again in Einsteinian way of looking at it. And how does the equation force equal to mass times acceleration change when you look at it from Einstein's perspective? How does acceleration change? How does velocity change? All these quantities you want to know. So that's what we will do from the next class, or maybe even later in the class today. So let's see how far I can go. So this, we can call it implications of Lorentz transformation. Notice the logical flow here is that Maxwell's equation seems to have suggested that there is a speed that is a constant, in the sense that you go from one frame to the other, it doesn't change at all. So there is a constant speed which we associate with speed of light in vacuum. And that statement in principle requires that the relativity principle is governed by Lorentz transformation. And if we keep everything one-dimensional, say Z is what we do. So this is Z prime, CT prime, that's just for dimensional reasons. And things can be put together as a matrix transformation. That's theta gamma, and that's gamma. That's your Lorentz transformation. Of course, it's understood that things are all in one dimension. That means y prime is the same as y, and x prime is the same as x. In principle, you can make this as a 4 by 4 transformation. I should also say that the simplicity already one dimension has, even though the transformation is very linear and simple, the effects are not at all straightforward. It's almost very surely counterintuitive and often paradoxical. Like there's a lot of paradoxes you can construct, or seeming paradoxes you can construct. But I should also say that two-dimensional gets much more richer in the sense that it gets what's the word? It gets mingled, I think, is that the word? It gets mixed with rotations. For example, you might have heard, like this is again a popular level. I won't be, actually I do address it in your homework, right?
Yes.
In your homework, there is a problem where it says that if you have a Lorentz transformation in the x direction and a Lorentz transformation in the y direction, that leads to a rotation. Yeah. So I'll leave that in your homework. So I won't go more than that. And there are a lot of paradoxes you can build in that, or there are paradoxes usually in that context, and it's nice to think of it in that form. Maybe I should just mention it just for, I mean, sometimes I feel these are the things you take home and you should think about it. The courses, of course, you will take. But yeah, so the point is the following. So this is one of the paradoxes you build, right? So you have let's say, a train. Yeah, so there's a train, and this is a window in a train of a certain length. And let us say it's going with velocity v. And you try to throw you want to, and there is also a stone which is exactly of the same length. So if both were at rest, then this length is exactly the same as this length. Right? And this could be V1, and this could be V2. So let's say this is moving in that direction. And naively, you would say that since V1 is moving, as we are going to see today, length contracts, and these results probably you have heard before. So whenever something is moving, things contract. So with respect to this frame, this would contract. And so V2 will say that, oh, I cannot go through. Like, why even try? I'm not going to be going through. But when it comes to V1, if you're an observer here, this will of course have this velocity, but this will also have an opposite velocity V1, right? With respect to this, it is moving in the backward direction. And he would say that, oh, because of this velocity, this will contract in, so that will go through. Those are two different physical processes. Only one can happen. Either you go and crash into something, or you don't crash into something. It cannot depend on who is seeing, who is watching. Right, that's a wrong, like it cannot, that's a paradox immediately, right? So which one is true? So these were actual real paradoxes that came up against the theory right in the beginning. Imagine historically when you give this theory, it's cool, nice things are being said, but then there are these paradoxes. So it can actually bring down a theory. But then this was carefully analyzed, and what the conclusion is, what is the understanding is that actually, this is not when for this observer, this is actually not that there are two velocities. So of course this will contract, but this actually gets just twisted. So when it is going through this with one of the frames, this actually rotates. So two Lorentz transformation also rotates, leads to a rotation. So that's a very interesting thing, because there are three rotations, remember. And rotations are also not commutative, remember. Maybe you have seen this, maybe. So let's see, online, okay. So this is Moses' assignment, okay. So what I'm going to do is, that's your z-axis, and that's your x. Let's say my right hand is the x-axis. Right? The forward direction is the y-axis, and the vertical direction of this paper is the z-axis. You guys might have seen this. So I'm going to perform 2 rotations in opposite orders. Okay, so first I start from here, and I first rotate about the x-axis, 90 degrees about the x-axis. Right? So that's 90 degrees about the x-axis. If you remember, the x-axis was my right hand. And now I do 90 degrees about the y-axis, positive and negative possible there. I'll do the y-axis this way, right? Okay, and now the sheet of paper is facing my left side of the board on the left side, and the vertical side is facing, let's say, you sitting in front of. If you remember this configuration, now let me begin again. Okay, so I'm going to begin again. Do the opposite now. First, I will rotate about the y-axis 90 degrees. If I remember right, I think I rotated. So I think earlier we did x-axis, right? So we did x-axis, and then I did so I went that way, right? So with respect to me, the clockwise. Okay. So now I do the y-axis first. So that's clockwise, right? And now do the x-axis. I do this, and clearly it is facing down. So the configurations are not at all the same. And this even holds if you do infinitesimal rotations. Okay. This the conclusion is that this is the effect that leads to the, in quantum mechanics, you have L1, L2 minus L2, L1. It's not commutative, right? These are all related to that. So these are, that means to say that you can now reverse it also, right? I go 2 steps and then come back 2 steps in that same order, and I might not reach the same place. Right? So these are effects related to that. And similarly, now these are rotations, right? But Lorentz transformation are also now boosts. So you first make a reference frame. I go with velocity 1 in the x direction, then you do velocity v2 in the y direction, and you do the inverse of that. That's not the same. Right? It depends on what order you do, and that's the effects that lead to paradoxes of this kind. Okay. But this really doesn't happen. This is unlike twin paradox, where one gets younger and one gets older. That sounds like a paradox, but that's really true. You really get young, so there's no paradox. There, the paradox could be that, okay, which one is moving? I mean, who is moving actually, right? That could be the paradox, because movement is now relative, right? And then you say that, okay, the only way you can check is that you have to come together. For that, someone has to accelerate, and the moment you accelerate, then you have to bring in other factors. But the time difference is a relative concept. How old you are is with respect to you in your frame, and how much I measure your age is not the same. It will never be the same. Whether you accelerate, you do whatever you do, we will be in 2 different frames altogether, and overall the amount you add up will not or need not be the same. That's relativity for you. That's kind of the summary of the big punch one. And one more thing I wanted to say is, again, as what you want to take home in relativity is whatever I just now said, the time and space or distances are not the same. Notice that if you are doing, let's say this is x and y quantities. This is the counterintuitive part of relativity. So there is x and y, and let's say there is this length here. That's the physical distance there, and we know that. So this is the actual rod. That's the actual physical rod, let's say. And now think of sunlight falling there. So let's say there is sun here. I'm just making a story around that. So there is sun there, and there is a shadow formed, and that's your shadow. It is, as you can see, this is a component of that length. Like if you think of it as a vector, that's a component. So this could be the A. And now let us say that you rotate there is some rotation here. So you rotate this. Right? And this is your new X prime, and that's your new Y prime. And if you were to measure again the X component of this won't match. It's not expected to match. And you won't be surprised at all. Right? Oh, shadow, why should it be the same for different references? There is no, intuition doesn't stop you at all. And that's how you want to look at Lorentz transformation also. So Lorentz transformation has distances and time. So time is usually put on the wording. So there's distances and time. There is nothing special about time. Right? If you measure time, so this is now again an event. Let's say this is an event. Now you say event because it's a position and time, right? It's not a distance. So this is an event. Now you can take a projection in this. Right? Projection is the time that you measure. This is the length that you will measure for this. Time has nothing special in it. If you change your coordinates, time will change. Right? Because it's just a component, right? This is a component of a vector. What remains the same is z squared minus c squared t squared. This quantity remains the same. So if you want to compare ever, you want to compare this quantity that remains the same. And that's what we want to do for the whole. So we want to rewrite our introductory physics course in terms of quantities that do not change. That will be our goal. Right? Everything, velocity, acceleration, force, energy, momentum, everything that we have seen, and we will do that in a lecture or two. It's very easily done, and that's what Einstein did, that don't talk in terms of the entity. But everything will remain the same. I should not, it doesn't mean that you're changing quantities. Velocity will remain the velocity. You're not going to redefine most of the things. Most of them will remain the same, but we won't compare it. When I'm talking to another person, we won't compare distances. We won't compare time. We won't compare velocity because velocity is not invariant or doesn't remain the same. So we will find quantities that remain the same under transformation. That will be our goal, and write all the equations in terms of that. Hopefully that gave you an idea of motivation of what's going on in a sense. Christian, comment? Nothing? Okay. Okay.
So you have the first graph as like a spatial y and x. That's called a shear transformation, right?
That's just rotation.
If it's just space, then it's just like a shear. And then if you add time, it's called the boost. That's what the boost transformation is.
These are called three boosts. So these are three rotations. These are three rotations. These are the three boosts, three independent boosts, X, Y, and Z. And what else is there? There are three translations. That's a fundamental transformations that we talk about. There are three translations in space, and there is one translation in time. So there are 3 plus 3, 6, 9, 10. These 10 transformations together is what is called Poincare group. I think that there's some accent there. And I'm sure I'm not saying it right. So Poincare group. So that these symmetries pretty much govern a lot of physical principles. Are you guys familiar with this? No? Okay, so I can tell this. Look at how about this quiz, right? Poincare groups and related. So I try to tell this here and there, but details are not possible for me to go through. So here is a simple summary. So this is the content of Noether's theorem. Again, I think I'm not saying it correct. German word is Luther. I think Luther's theorem, something like it's a she. I think in the early part of 19th century, she pointed out that whenever there are conserved quantities, like energy is conserved, momentum is conserved, so important energy conservations have a symmetry associated with that. So you take a physical system, and if there is a symmetry under translation, so that's a time translation. So what do we mean by time translation? So we are sitting here, and let us say, magically, at least theoretically, it is possible. You can imagine that suddenly the whole world, the whole system, everything around you is transported in time, let's say 20 years down the line, or even 1 hour down the line. And the question is, would you know it? Is it possible for you to realize that translation in time? If you can, that means you don't have the symmetry. That means energy is not conserved. If you cannot notice it, everything looks the same. It's the same equations that is governing you earlier, even now it is the same. If everything is the same, so time. So if your system is invariant under time translation, this means energy is conserved. Otherwise, energy is not conserved. Okay, so very big statement. And then you have space translation. So there are 3 space translations, right? So 1 time translation, 3 space translations. So again, ask the same question. So this room, let us say, let's take a closed room, that makes it easier. You have this closed room and everything is moved for you. Like the room is moved, you're moved, every table is moved, every atom in this is moved by 1 centimeter, or let's say 10 kilometers. And the question is, would you know it at all? And if you can observe the difference, for example, if there is gravity, usually you can, if there is something external, then you would know it. That means that the linear momentum is conserved. And remember that linear momentum has to do with external forces acting on it. So very easily you can check these things. So this is linear momentum, 3 linear momentum. Right? Linear momentum is very strong statements. And then we have 3 rotations, right? And what is the quantity associated with rotation? Yes?
Angular momentum.
Angular momentum, that's correct. And of course, we have 3 boosts. And I'm wondering, what is the quantity that's conserved? What?
So a boost would be like a squeeze and a stretch, right? Because otherwise you would move faster than the speed of light. So your translation would have to be like.
Yeah, you mean to say squeeze and a stretch in time, right? Stretch in time and squeeze in.
Yeah.
That's right.
Otherwise,
Yeah.
if you just do a linear transformation, you'll have speed of light would increase as you changed your axis.
No, it depends on the physical quantity you're talking about. For example, acceleration. So I think what you're suggesting is that, right? I mean, you're right that if it is speed you're talking about, it has to be in this cone, right? I'll talk about it. I mean, I'm jumping ahead. But you seem to be suggesting that nothing lives in this cone. Right? That's not correct. There are things that live. For example, acceleration will live in this cone. Okay, so there are space-like objects, physical quantities. It's just that if you're one space-like, you're always space-like. That's the only requirement. And I'll give an example again that has to do with simultaneously. I will go there. So yeah, you don't, but you're talking about velocity. Your statements are all correct, but I felt there was a suggestion that maybe you cannot have something in this, like this distance length other than the time, like this is v, this is time. But it depends on what quantity you're talking about. If I'm talking about acceleration, I would say this is the zeroth component of acceleration, and that's a space component of acceleration, and then acceleration sits in the other frame or in the other cone. Okay, so yeah, small. What is a conserved quantity related to boost?
Is it like z squared minus ct squared? That one.
No. No. Sure. No, because that's it. Yeah. Yeah, that's an invariant length. That's like saying the distance is invariant here, but angular momentum being conserved is much more. If you're doing mechanics, you have to go to the action and talk about the Lagrangian doing this thing. So it's a much more, the Noether's theorem is much more richer, deeper than the invariant length. And here it is, I think it is the center of mass. Yeah, quiz. Quiz is not invariant, but this is a quiz. Yeah. Okay. It may not be easy to find. I don't think it is very popularly there, but if you look at Schwinger's work, he stresses on this, and I can see the equation, but I'm not able to say it the right way. Yeah, and this whole thing is called point correct group. And that deep connection. Okay, so I should proceed. Okay. Okay, we said that that's a Lorentz transformation, and there were some discussions that came up with space-time diagram, and one of the things so this is a space-time diagram representing this. So this is T or CT, and that's C. Recall that based on this transformation, we said that z squared minus c squared t squared is equal to z prime squared minus c squared t prime squared. And usually we always want to think of it like we do this in vectors also, right? Always a vector is a difference between 2 points. Often we keep one of the point at the origin and talk about just one point. So when I say z and t, that means that the other point is the origin. It's with respect to the origin. So you always want to talk in terms of differences between points. That gives you more or leads to less confusions if you want. What does this mean? Where are these points? This is on a hyperbola, right? So there are these 45-degree lines because of the dimensions we have chosen, CT, and this is and this equation of a hyperbola will be like this. So what that means is that the z and t, if this could be, even though I use this the same thing, right? So z and ct. So that's a point, right? But then I said that you should always think of it with respect to the origin. So that's a vector. If you want, that's a two events. One happens at the origin and the other happens at the point Z and T. And the Lorentz length of this is, the length of this quantity is Z square minus CT squared in this metric. That's clear. If you go on any other point here, right, so let's say here it's very visibly different in length, right? If you were to calculate this, Z prime and CT prime, same quantity. Each of this point, the length of this vector, not the usual length that we associate in this sense, like Z squared minus CT squared, for every point on this line will be the same. That means that when you're doing this relative motion, you're actually moving that point somewhere here. If you know that your observation point is somewhere here, every person in this universe who is moving relative to you will measure it somewhere on this curve. It may not be exactly this. The length, remember, is the vertical component. They will measure different lengths, but they will all measure the same total length. Invariant length will be the same, but the time they will measure will be different. Same thing on this. It doesn't have to be on that part of the cone. It could be here. These two are the same quantities. They will all be the same. So whenever you move around, so the key point is that geometrically, whenever there is a relative motion between two objects, the coordinates go along this hyperbola. Pick your hyperbola, pick the one that is there. First, it decides where that point is, and it will always be on one of the hyperbolas. And that gives you a lot of conclusions you can make now. And the first thing we'll talk about is simultaneity. Oops. So let's talk about simultaneity. And what happens to simultaneity in relativity from your earlier courses? Let's say there is a statement that if I can use, like, let's say Luke and Moses, I don't know whether they were born on the same day or not, but if you allow me to use that as an example. So Luke and Moses were born on the same day. Okay, so that's a statement I make, but that's a useless statement. Okay, in relativity, if you bring in relativity, that's a useless statement because that says something about simultaneous events. But simultaneity is completely relative. That means to say that what looks simultaneous to me need not be simultaneous to someone else. Okay? In fact, it doesn't even have to be simultaneous. Again, let's take the example, like both were born at the same time, and we could say when Moses was born, someone shot a gun, and when Luke was born, that same bullet came and hit someone else sitting next to Luke. So there's a cause and effect there, right? So if this was a simultaneous event, one would say that, oh, in another frame, one has to fire the gun first, and this has to happen. But simultaneity can be changed. It can be made positive or negative. How does this happen? So let's look at this diagram again. So let's say most of the things can be got from a diagram. Okay. Now let's say things are simultaneous. Again, let's have a reference here. There are two events that's happening at the same time. So let's just for convenience choose it to be the t equal to 0, but can be anywhere, right? Right. So that's your 2 points, right? They have the same. They happen at the same time. If you see horizontally, they happen at the same time. Or actually, better, let me make it 1 at 0, right? So changed. Right? 1 could be at 0. That makes it easier. Now, right, the length of these two vectors would be, let's say this is 0, 0. And this could be time is, so z and t, 0, right? So it is space-like anyway. Now, if I were to move things, right, we can say this is, that length is dz squared minus c dt squared is equal to dz prime squared minus c squared dt prime squared. This is valid. If this is true, this will also be valid. What I've chosen in this is that the time difference is 0, so that's equal to 0. And that's what simultaneity means, right? The time difference between two events is 0. That's what simultaneity means. But if I change my reference, or if I move, I am in this frame now. I created a dt prime. So it's not simultaneous. What happens here is that I can go here. This is equivalent to going anywhere on this hyperbola, and I have moved. Like either I can say there is a literal v I can provide and say that if you go with a certain velocity, this is what your new distances and time is. But on diagram, that just means that I'm moving along this trajectory. For this part, so these two, 1 and 2, were simultaneous. 1 prime and 2 prime, 1 prime, the same 2 points. Clearly 2 prime happened later than 1, right? It's in the future. As if you look at the time, 2 prime is in the future. But we also said that there is another point here. This could be 2 double prime, and that could be 1 double prime. That's also the same. As another observer that sees that, oh, 2 prime happened before 1. So the order of events chronology is completely, if the word is completely, or there is no absoluteness in it. But as far as our world goes, we do see order in it, and that's called causality. If something happens before something else in one frame, it happens so in every other frame, to our knowledge at least, in every experiment and to our understanding, mostly because whether we can comprehend it or not, it is causal. Everything that we do is causal in this. And simultaneity is not an absolute concept, it's a relative concept. So we have to give up simultaneity. So there is no such thing as simultaneity in special relativity, which means in real life. Right? Simultaneity is meaningless concept. You can make it philosophical, right? You just have to go fast enough, and there is nothing called simultaneity. Right? So very strong statements. Should be.
So based on the Lorentz time variable, where you have like c squared in the denominator, and then the x is multiplied by that, you have to be really far apart in order to see any sort of change like this.
Oh, no, this is possible, right? Okay, how can you make this? You want a real life scenario, right?
Just because your equation is v squared divided by c squared.
Oh,
So
yeah. That's correct. Yeah, because c is so large, you're saying, yeah, z has to be extremely far apart and to get these effects useful. Yeah, you're right. I think, yeah, very good actually. You're trying to, that's a good point. So if you write this as z squared minus dt squared, right, that's equal to a constant, correct? So if you want to really see this effect and to move things around, then probably z has to be significantly larger than c. Yes, you're correct, I think. Yeah. But there are easier ways to see this actually. I'm thinking, what's the immediate thing that I'll think about it. I don't know. Yeah, because can you come up with a place where simultaneity is not obeyed, right? That's what it is. In one frame it is simultaneous and the other frame it's not. Yeah, come up with an event which is not simultaneous. But let me not. Okay, another thing, as you counterintuitive things, right? I think I won't be able to finish my lecture. But length contraction and time dilation, you all see it, right? Maybe I'll skip that. That's what will happen because you see it somewhere or the other. But or maybe I'll just do it very quickly. Okay. There's one more thing, interesting thing you can do, and again, simple logical conclusion gives you this. Notice, let's say, if you're just sitting at a point, so this is time, and that's your z. So there is an object just sitting at z equal to a constant. And nothing, it is not doing anything, it's not moving with respect to that particular, the frame that I've drawn. It's just sitting there. How will it look like? Its z will stay the same and it will evolve in time. This is called the world line of particle A. So that's a world line of particle A. So in a space, so this is called a space-time diagram. In there, how the particle is evolving in time is the world line of a particle. Of course, if you stretch it backward, assuming that it was staying still all through, it goes backward. Think of our planet, like our planet, if it was at rest, or if you're sitting on, your planet, with respect to you, you're at rest, so it's just staying there. In that particular frame, it's just a straight line. That's your planet's world line. Right? Now there is another planet, let's say, here. B.
Would you mind rotating the board back?
Oh.
You don't have to repeat yourself. I think if we see it, we'll get what you said.
How did it go away? Oh, I think I pressed the wrong button. Okay. Yeah, so there is a point A in the frame which is at rest. So if you're at rest, this is just a world line that keeps moving. It's a straight line in there, right? Let's say there is another point B. This could be another planet relatively far away. As Jordan pointed out, that if you want to really see these effects, either you increase the distances significantly or you decrease the speed of light. So that's harder. Speed of light in vacuum is hard to change. Or you go into a medium where the speed of light is small. Right? In glass, light travels a little slower, like very little, tiny bit slower. So, but you can find medium where it gets more and more slow. Refractive index, remember, is the measure of speed of light in the medium. So if you have a strong enough refractive index, but not much, diamond is the largest we have among natural materials, and it's only a fraction of it. I think it's 4 or something, right? So diamond's refractive index, I think, is 4, maybe 2.5. It's not much, only 2.5 times smaller than speed of light. Anyway, so there's point B here, significantly far away, and it is also rested. Let's say, let's make it simple for now, and that's what is happening. But now notice that if A cannot see B directly, right? So it has to be through light. So what happens? So if they have to communicate, imagine you're very far away when you're on Mars, right? Imagine communication in Mars, how it's when your friend goes to Mars, let's say Moses reaches Mars and he has to communicate with Luke, how is it going to happen? It won't be immediate. How much time does it take from here to Mars? For a light signal to reach? From here to Sun, it is about 8 minutes. Right? From here to Pluto, it's about 6 hours. I think Mars is, if I'm not wrong, 3 minutes or something.
I thought it was either 8 or 12.
8 is sun.
Yeah.
8 is
I
sun.
know,
So
um,
probably not 12 because sometimes Mars is closer than. I don't know actually.
I think
Is
just
it 12?
because we recently got a rover to Mars,
Uh-huh.
and I think
It took 12 minutes for the.
some sort of effective communication time was like 12 minutes, but that could be like processing as well as.
Mostly it is a distance, I think.
Yeah.
It is dominated by that. So it might be 12 minutes.
I might be wrong.
Yeah. So anyway, so it is far. So it's in the order of minutes. So imagine you say hello, and then you wait for 10 minutes. Like that's a conversation that's going to happen. You wait for 10 minutes, and then the person says another 10 minutes. Right? So it has to go there and then reacts to that. So it takes 20 minutes for a linear chronological conversation to happen. So how does that happen here? So a signal has to reach. So, but there's light, right? Light cannot go faster than so. How does light go 45 degrees? Right? That's light. Right? I meant 45 degrees, right? So that's light going. So whatever B communicates at time t equal to 0 in this frame reaches A at this point. He or she, again, assuming that sends a light signal, goes this way. So that's how communication happens between two world lines. Right? And you can keep going like that. That's a linear one after the other. The simple idea here is that if you want A or B to see anything that A has done or to communicate, you have to come in the light cone. So again, I'm going to draw a new figure. So if B has to communicate with A, so there is A has a light cone. So this is what is called a light cone of A. So let me say, so this is light cone of A. At a certain instant, at each instant, you have a light cone. If you want to communicate with A, you have to come in its light cone. Otherwise, you cannot communicate. Or I use the word communication, even if you have to interact. Interaction happens at the speed of light. If you want to have anything to do with A, if you want to even know that A exists, you have to come into the light cone. Think of the universe. This has big implications. Is there a universe out there beyond? Is there a surface to our universe? If light cannot come inside our universe, we don't know what's there out there. And remember, light travels a certain amount in a certain distance. So there are huge implications of this. So this is the light cone. If B enters here, then we know, then there is a chance. If you go fast enough, then there is a chance that this information reaches them. So that's one thing. So let me give you an example in this way of two objects moving in the same frame, but at least at some instant, they won't be able to see each other. Okay, so let's so here is again a space. So this is a reference frame, and this is okay. So now let's say this is actually a hyperbola. I claim, or if I were to tell you that this is the path of a particle, this is the world line of a particle. Is that possible or not? This is Z, and that's Z times T. World line of let's say B. Is that possible? Is there anything that stops it from not happening? In these kind of questions, the only thing you have to check is that is it ever, the slope of this line, is it ever going more than 45 degrees? Right? That's all you have to check. That's what I mean by that question. And notice slope is, the slope has to be in within this light cone, right? That's what we are saying. So at this point, so draw a light cone at every point, right? That's a light cone. That's within the light cone, right? It's inside of the light cone. Draw another point here, light cone. Yeah, it's inside of the light cone. And however far you go, even when it is really tangent to that, I'm within that light cone all the time. And as far as you're within the light cone at each point, that means it's a valid world line, right? So that's a valid world line. That could be a real particle moving in the, and this happens to be a, like we have not defined constant acceleration in this new Lorentz space, if you want. But once we define what is called a constant acceleration, this will be the path of a constant acceleration. Okay, so that's there. Now there is another particle also going with similar path. So notice, by the way, this arrow represents that it comes from the past and goes into the future. You cannot come from the future to the past, right? Or we're not talking about that. At least we don't know. Okay. Similarly, there is another particle that's doing this. That's A. And this could be really close. I just randomly picked a curve like this. I can make this really close. Now the point is, the question is that can A send a signal? Can you imagine A sending a signal that can be received by B? It has to be light. So if you are in the very past, the best you can do is this. That's the light going from A, when A was born, let's say, very much in the past, and it goes that way. It doesn't touch here. This is also a light sent by A. It doesn't touch B. So these are all light being sent periodically by A, but it never touches B. So this could be a universe, or Z could be a universe. This part, so B, never sees A. So certain part of the universe never sees and never interacts. There could be two particles there, and they won't gravitationally know each other. They won't even feel each other. Right? Gravity requires signal to go at the speed of light. So those are implications of such a space and time. Very counterintuitive. Like you will never expect that. So if we are talking about that, could be someone right next to you, right? This could be a very small distance in principle. Right? It could be very small. But then I won't see Moses either. That's all. If there is, and actually, no, I should, yeah, no, it is correct, right? Yeah, it's correct. I think you can have to, yeah, think about it. It gets messy very soon. Am I saying that I can be having an unknown thing here? If it's moving with a certain, because there's a time piece here, right? If it has to be moving in a certain way. So that's, if a certain object moves in a certain way, comes very close to me, doesn't touch me, but almost comes next to my cheek and then goes away, and I won't know. Something like that. Yeah, I think about that. I might be making, in the simplifying things, I might be making wrong statements, but you get the point, right? The non-intuitive part of it. Okay, so that's some of the arguments, and these are the kind of arguments we always use. You don't want to really do the calculation. You just keep this the same, go around on this curve, and you can get most of the physics out of it. Ideas are there, and then algebraically you verify. That's how things work in this geometry. Okay, but let's do some concrete things, or similar. These are all concrete, by the way. Nothing non-concrete about it. Let's do the, what I meant was to do the standard things that we see in undergraduate physics. Let's say there is, so this is length contraction. First, let me say time dilation. That's easier, I think. time dilation. Or not easier, just cleaner, or less room for error maybe. Okay, so we are measuring difference between two events and measuring the time, right? And as I said, it's going to be relative, so we should accept that. But then, what kind of relativity is it? So we measure two events. There is a length difference in one frame, and this is a time difference in the other frame. So this is the connection between the two. This is velocity dependent quantity. And the same quantity measured in another frame is this. Now, whenever we are measuring time, so this is at this time, we need to talk about what does it mean to say measuring time. So is there something special you want to associate with that? We will say that in the rest frame, so for example, if it is my watch, right, then it is at rest with respect to me, right? My watch is at rest with respect to me. And in that sense, its position is the same at every time, right? At t equal to 1, it's at z the same. T equal to 2, it's at the same. So with respect to me, the position of the watch doesn't change. So there's something special about the rest frame. And let me say this is the rest frame. This is the rest frame in which the time is measured. And for this particular measurement that I'm doing, delta z is equal to 0. This is a very special measurement. This is not for any time that time dilates. It's a very special. There is two events that happened that I took a watch and took the watch's position, right? It's not any random event we are talking about. It's the position of the watch that we are doing, but you can associate it with true things also in that sense. You can generalize this. So this is the position of the watch, and this is the time I measure. Since the watch is at the same position in that rest frame, so that's equal to 0. That's the conditions we put. Now, once you have that, now I can immediately say what is c dt prime. So if I say in the new frame, I don't care what delta z is, that would change. But what is c delta t prime is equal to gamma times c delta t. Forget that c's cancels on both sides. And remember, beta is equal to v over c. It's always less than or equal to 1. And gamma, which is equal to 1 over 1 minus beta square, is always greater than or equal to 1. Right? So this time that anyone else measuring a time will measure a time difference larger than the time that is measured in the rest of frame. So this is called time dilation, right? You cannot escape. Okay, so that's, any questions around that?
Just one quick
Yeah.
question. We're setting delta z to 0 because it's the rest frame, not a separate condition. Like that's
It is a separate condition.
okay. So
It is a separate condition in the sense we are describing the event here.
Mhm.
We always have to measure 2 points in coordinate system, and these coordinates happens to be of the same watch. Right? Take the watch, find the position of it at t equal to 0, and wait for some time, and again find the position. But with respect to me or with respect to the watch, its position is not changing. So that description of the two events puts me there.
Okay.
But it's not for any two events.
So
It's not because it's at rest. Probably it is at rest. For any two things at rest, this will always be valid. Probably.
okay.
Think of you measuring your position of of your notebook, of your eraser that's sitting in front of you, its position will not change. Right? So rest frame has this implication that that goes to 0, and the moment that goes to 0, time measured by anyone else will die.
Okay, so the delta Z is a between two events.
Between two events in the rest frame.
In the rest. Okay.
In the rest frame. So yeah, it is a rest frame property that is being invoked here. Yeah. Okay. Okay, so that's time dilation. As length contraction, this is slightly less neat if you want. At least to me it is less. Okay, again, let's do delta Z. So now I have to define a new way of measuring things, or two events, gamma, beta gamma, delta Z, and C times delta T. Okay, so now we want to talk about, so that is length, right? So there is a rod, real rod, right? And we have a frame, so there is one frame that is moving with velocity v, and there is another rod which is at rest. But this is the rod, physical rod. And you want to come up with a way to measure its velocity, and you say that, oh, if I'm at rest, now if I'm in the rest frame of the rod, then I can measure. So what does it involve to measure the length of the rod? I have to measure this length, this point here, and I have to measure this point there. So that involves measuring Z1 at some time and Z2 at another time. Right? That's a possibility. But is that what you want to do? And you might say that, oh, since simultaneity is not well defined here, so how do we make a rule for measurement of our distances? So here is the rule going to be. So if you're in the rest frame, I don't mind at what time you measure it. But if you're in any other frame, you have to measure it at the same time. So that's a way you're going to measure distances. Okay, so this is what I mean by you're imposing a condition, but that's what it happens whenever you have two events. First, you have to define your event. So in this definition of defining the measuring the length, we are going to say that if you are moving, then you have to measure it simultaneously in that frame. Remember, simultaneity in a frame is well defined. It's just that you cannot compare. All right. So, so if you are in the rest frame, you can be whatever you want to do. So let's again say one of them is at rest, right? So in the moving frame, so this is let's say this is rest frame. Or the rod's rest frame, right? Rod's. And things are moving, and in that moving frame, I have to measure it at the same time. This, I will put this to be 0. Okay, that's the what do you say? That's a description we are making for the events. And now let's see if I set all this correct, it should come out as a contraction. Let's see. So now I have to measure delta Z, right? So it's not very convenient to do this. I have to invert this, right? So if I invert it, I can actually get delta Z much more easily. So I'll write this equation as, let me move things around a little. So inverting this gives me the inverse of this matrix is what? What's the inverse of this matrix? The inverse of
minus
Lorentz. Yeah,
Minus beta gamma, minus beta gamma.
that's correct. The only thing you have to do is put a minus sign in the non-diagonal terms. Okay, that's very convenient. So that means to say that if this is, when this is at rest, you say this, but if you invert it, that means to say the other person is moving backward, right? That's how it looks like. So that's the minus velocity coming in there. But you can check, again, that's too many quiz problems. Quiz is that find the inverse of it and check that the inverse times this is equal to 1. Okay, so find the inverse of this matrix. So gamma, beta, minus beta gamma now, minus beta gamma, and gamma times delta z prime times c delta t prime is equal to, am I still on the board? Yes, so it's delta z times c delta t. Is that algebra clear? Like I multiplied by the inverse matrix on both sides, this one will give you 1. This makes it easier to use this condition of 0 easily. Right? Gamma times delta z prime is delta z. So gamma times delta z prime is actually delta z. So which one was at rest? It was the z that was at rest, right? So it is the moving frame measures the length as delta z prime, which is delta z over gamma. Gamma, remember, is greater than 1. So whatever the rest frame measures, it will be contracted because gamma is greater than 1. Okay. So that's length contraction. Okay, question, comments, anything? Yeah.
So what happens if you like vary t with the same position? Like instead of a length contraction, you have like a time contraction.
But then you're changing your physics, right? Remember, we were talking about time contraction. Time means it has to do with the watch, right? Watch has to be kept static. So first you have to define the two events very properly. It's not a transformation you always go through. So this setting equal to 0 is part of that definition. Like, what are we measuring? What are we trying to do here? Right? You see what I'm saying? So if you say CT equal to 0, then it may not be time that is dilating. It might be something else. Because earlier we had to set T in the right place to be 0. Or again, that was regarding the watch that I was talking about. Is that clear? Probably I have not addressed your question. And I roughly know what you're asking, but yeah, I don't know the answer about that. Yeah, I roughly know what you're asking. You're saying that why it seems like I'm cheating here. I think what you're saying is that I'm fudging by putting the zeros in the right place. So it seems like you can get another result, which if I put this equal to 0 on the other side, I can get the opposite result also, right? Yes, you're right. But one has to be careful about interpreting what you have in hand. So I'll leave that to you. And you guys, you criticize whatever is going on. Is that reasonably satisfactory, Jordan?
Yeah, that's kind of what I was asking. But it seems like you could have, yeah, that's good enough.
Yeah, I'll let you figure. I mean, it is there. I don't deny that. Yes, it seems like that, and you should criticize it. But let me not do it here. I will myself get confused. I mean, I keep it in a very. It is sensitive to these arguments. But if you allow me, since you guys offer to me to take extra time, right? So I'll do this is the velocity addition because we need it for the homework. So I'll finish that also, and then I think it can be done quickly, hopefully. So, okay, so let's say we have this is an interstate road and things are happening. Two things are, so there is a rest object. So this is at rest. So this person is at rest. And there is a car. And that's the best I can draw. Right, that's, let's say, A. And it's going with velocity VA. Right? VA. And there is another car all going straight line. B. That's also, it doesn't have to be moving in the same direction. That's B. And all these people are seeing something happening here. So this is the event. If something is happening there, that's a coordinate system if you want. Right? Clearly, let's say this is Z. This could be ZA. And there is a corresponding time also, right? TA. And this is ZB. And of course, there is one AB also here, right? With respect to A, what is C? So something. So let's say, how does the coordinate and time measured by this ground observer seem like to be to A? So there is Z and CT. These are measured. This is the coordinates measured by ground. Measured by ground, G. Since A is moving, so this is beta, so this is A. Right? Since A is moving, this transformation gets transformed. That's A, beta gamma A, and gammas are hard. And that's equal to ZA CTA. These are the coordinates of this event measured by A. These are measured by A. Okay. Same thing, B also measures something, and on the board. So there is ZB CTB, that's equal to gamma B now, because it's moving. Beta, beta and beta B. Of the same one. That should be correct. And now let's say, what did I want to do? Yeah. So I can ask, right? I can ask, how does A's coordinates look like with respect to B? Like something measured by A, how does it look like for B? So for that, what I'll do is I'll substitute this in there, right? So I will substitute it in there. But I know how easy it is going, what it's going to look like. I just have to move this matrix on the other side, right? And that is just by changing this beta to minus beta. So this is equal to gamma A, beta A A, beta A, gamma A, that's just copying. But this is equal to this times this in the inverse sense. That's another matrix times ZB CTB. That's how the coordinates measured by A looks like to be. And what is this? That is gamma B minus beta B gamma B. Okay. And if you allow me, can I erase this? I'm going to erase this part so that I have space. This can be processed, right? So this can be processed. So let's multiply this out. So it's gamma A, gamma B, and so on. So, right. So this is gamma A, gamma B times 1 plus B. Oh, this is a minus, right? Sorry. Minus. 1 minus beta A, beta B. Okay, that's the first term. This times this times this, gamma A, gamma B is common. So it's gamma A, gamma B, and it is beta A minus beta B. Is this within the board?
Not anymore.
Not. Right. And this will come out to be symmetric. This is the same thing in here. Gamma A, gamma B, and beta A minus beta B. And this is gamma A, gamma B, 1 minus beta A, beta B, right? But this is a connection between A and B. I could directly look between A and B and ask what is the relative velocity. Right? Whatever is the relative velocity between them, that should be what this should be. And let's call that the relative velocity to be just gamma. This has to be some velocity, right? Between A and B, there is some velocity. Like that's that relative velocity, which comes out to be having this algebra. But there is, if I were A and B is raw, is moving, I know that he's moving with some, I'll measure some velocity, and that's that velocity. Is that clear? The logic? Any questions there? If you accept that, that means these two will be the same. Right? That's the relative velocity is given by this formula. I have a relation. So I know the algebra then. Right? The connecting the velocities. So I say gamma has to be equal to gamma. So the two relations you can think of, gamma is equal to gamma A times gamma B. Right? That's times 1 minus beta A, beta B. That's equating these two. There's another one I can equate these two. Right? So similarly, beta gamma is equal to gamma A, gamma B, beta A minus beta B. Yeah, right?
I think you made a mistake on it. Shouldn't it be gamma A, gamma B, beta B minus beta A?
That again, which one? Here?
Am I wrong about that?
Is it multiplication wise?
Oh, maybe I made the mistake. I think you're right.
I think it's in you wrote beta A minus beta A.
Here, that's a confusion. Oh, this is beta A minus beta B. Yeah. Okay, yeah, of course. Yeah. Otherwise it's 0. Yeah, agree. But if this is the right, divide this out, right? If I divide these two equations out and let's say invert it, right, then I get beta is equal to beta A minus beta B divided by 1 minus beta A beta B. And that's often called the Poincare velocity addition formula. UREC likes to call it, but I think that's a good. So it's Poincare velocity addition. So velocity addition, remember what would have Galileo done? No denominator, right? That's Galileo doesn't have. And in the last 1 minute in your homework, there is a nice way of using this. That's what you have to do. You don't have to use this formula in your homework, much easier. So the idea is this. This was invented by UREC, a co-chick in the math department. So have a circle. And this is your line which measures your velocity. Okay, everything is on that line. This is the speed of light, c. So everything has to be less than that if you are talking about real particles. But analysis can be done for anything. In your homework, you will analyze things about, that's the best part of imagination, that you can imagine what happens if you were going faster than speed of light, like that's there. Let's say there are two velocities A and B. So let's say this is A and that's B. The way I have drawn it both less than C and both positive. But in principle, you can put A anywhere on this line and B anywhere on this line and use whatever. So if you want to do this algebra, what you have to do is first start from the North Pole, go through A, and hit the other part of the circle. So get this point. Start from the South Pole, go through B and hit the circle again. And get that point, those 2 points. Connect those 2 points. Wherever it hits on this line, remember that's your velocity, right? That's your relative velocity. And just by that geometry, you can always say that the relative velocity always will be less than c. So that's one conclusion you can immediately have. Now you can ask, if one was going slower than speed of light and the other person was going faster than speed of light, what will the relative velocity be? Right? Is there a general conclusion you can make? Those questions you can answer in your homework using this simple diagram. You can do it, of course, using algebra, but it's less insightful. This is much easier and you can do better. And I'll stop. Thank you. And thank you again very much for allowing me to take this extra times.
Thank you.
Thank you.
I have a question.
Sure, yes.
So we keep having problems in time dilation and length contraction where we're talking about quantities that, like we're trying to measure quantities that aren't necessarily like good quantities to talk about. So like,
When you say we keep
Yeah.
getting problems, what do you mean by that?
so like the question is, what is the length of the rod? Is not a good question because the length changes in different frames.
That's correct.
So that reminds me of like quantum mechanics when you're talking about if you measure this z angular momentum, what is the x angular momentum? Like that's not a good quantity to talk about.
That is different actually.
Yeah, I guess
Yeah.
that's what so like what is the good, so in quantum mechanics we say instead
Yeah.
of doing that, these are the good quantum
Yeah, no, actually it is very correct. I mean, because, yeah, you would say that don't compare X and Y because they're uncertain. Look for first find commuting variables.
Yeah.
Find things that commute with each other, and then it's okay to talk about them because measurement of one doesn't disturb the measurement of the other. That's pretty, sounds very much like this, but I'm not sure if there's a one-to-one connection there.
Right. It's not one-to-one.
Yeah, that's a good point. Yeah.
What are the good quantities to talk about?
Exactly. And that's what we will do.
Okay. Well,
That's what Einstein did. I mean, that was his paper. He realized this, and then he said that, okay, we won't talk about time dilation. He didn't, I think these are all the popular versions of it.
Right.
So he came up with the point that, okay, what are the quantities? So position is not a good thing. Time is not a good thing. There's something else. That's a 4 vector.
Mm-hmm.
But as he went through, he realized that energy and momentum. So at one step, you have to bring in the physics there. And that's where he does redefines one thing or two things, energy and momentum. He redefines.
Okay.
The rest, everything, he kept it as it is. And that's the implication of the easy bucket. The energy part. Energy has a rest constant.
So this question came from the question, like, is a world line invariant or like under different frames? Does that look the same?
No, right? World line will not be, because you can, this is the way it is defined, it is for this frame, right?
Yeah,
So it's,
that's true.
I think, no, it is not. It's not. So that's what you talk about. So the idea is that keeping certain, it can, how do you say that? You can transform everything on this picture into a new picture and still everything is fine. If you stick to certain rules, like Lorentz transformation rules. And that's why you will see many people, when you're doing special relativity, there will be these diagrams there, and they will replace it with boxes, like just simple straight line boxes, because in some sense you can always transform it and make it straight lines, and it's perfectly okay. Like, and yeah, that's okay. But world lines are not invariant. Yes.
Okay.
Right. Yeah. And it's like this line, for example, right? This is an accelerating line, but for B, it is a straight line. In B's frame,
I see.
I'm at rest.
Yes.
Right? It's a straight line. So surely it's not invariant. Yeah. I think that's.
Okay. Yeah.
But be critical. Like I might be making these statements. Yeah. But these kind of arguments are very common, like light going from one and reaching that. That's a very common logic that we see being used.
Okay. So my last comment
Yes.
is back to about Mars. Is we were having discrepancies between what the time of travel for light, but it really depends on the orbit, and that's
Yeah, if it is across from there, yeah, you're right. Because if it is beyond sun, then it will take more time.
yeah.
That could explain your 12 minutes.
I think
That you're across the sun.
every value that we discussed was probably correct at some point.
That's correct. Good point, very good point. Yeah, of course. It's not unlike Pluto. Pluto is so far that it is probably negligible where you are,
Right.
where Earth is in the orbit. Yeah, good point, very good point. So it could be 12 minutes, it could be larger than 8 minutes.
Yeah.
I was thinking, how can it be?
Yeah, because you want to launch the rover when they're closest. So that means by the time the rover gets there.
That's cool. Yeah. No, very good point, actually. Yeah. So some simple answers.
Right.
Good. Yeah. Okay, nice. Yes, Jordan, Alia.
Okay, bye-bye. I was just listening.
Oh, sure. Yeah. Alia, were you waiting or are you just listening? Yeah.
Yes.
Oh, just be a little louder, Alia. I think you're very, or maybe come closer to the mic, maybe. Yeah.
Yeah, I'm listening.
Oh, okay, great. Yeah. Okay. Yeah. You must have seen this before, right? I'm sure.
Yes.
Right? Yeah. So, yeah. Okay. Good.
Okay, thank you.
Okay. Yeah, sure. Yeah. Have a good evening, rest of the day. Yeah. Bye-bye.
You too.
Mhm.
Bye.
Bye-bye.